Hi everyone, I'm Dan and I'm going to present our paper, Single-Dataset Experts for Multi-Dataset Question Answering. This is joint work with Ben Dodge and Danqi Chen. This paper is about reading comprehension, where the goal is to build computers that can answer natural language questions about passages of text. For example, we'd like our computer to be able to answer science questions given a relevant paragraph from Wikipedia. Researchers have developed many reading comprehension datasets in recent years. For example, there are datasets with passages from different domains, or with different types of questions. Our goal in this paper is to combine them to build better models. Specifically, we assume we have one set of in-domain training datasets and another set of out-of-domain datasets. We'd like to improve in-domain performance on all of the source datasets, generalize well to questions from unseen datasets, and quickly adapt to new datasets given a small amount of training data. Our model is called MADE, which stands for Multi-Adapter Dataset Experts. Our main idea is to combine the benefits of single and multi-dataset models by modeling both cross-dataset regularities and dataset-specific patterns. We compare this to two lines of prior work. The first is multi-dataset fine-tuning, where the idea is to train one model on examples from all datasets. Given a collection of datasets, I, J, and K, we create training batches that contain examples from each dataset. We use a single parametric model, for example, a transformer, and we train the model to predict answers on this pooled dataset. Most prior work on multi-dataset QA falls into this category. For example, the multi-QA model, the submissions to the MRQA shared task, and unified QA, which is a recent state-of-the-art text-to-text model. One problem with this approach is that the model is prone to over- or underfitting different datasets. This was pointed out by previous work, which explored different sampling schedules, and we can illustrate the problem here, where we plot the validation performance from a multi-dataset training run as a percentage of the best accuracy achieved during that run. At this stage in training, the model fits news QA but underfits trivia QA. Later in training, the model fits trivia QA but overfits news QA. At the other end of the spectrum, adapters are a parameter-efficient way to train multiple specialized models that share some underlying components. Adapters are lightweight modules that are inserted in between the layers of a pre-trained language model. We use the standard adapter architecture, which is depicted here, and adds a relatively small number of parameters to the transformer. The main use of adapters in prior work is as a parameter-efficient alternative to fine-tuning. So the standard practice is to train single dataset adapters separately, and to keep the language model parameters frozen. This means it's hard to learn cross-dataset regularities. Our idea is to combine the benefits of single dataset and multi-dataset training to get a collection of Multi-Adapter Dataset Experts, which we call MADE. We do this by combining dataset-specific adapters with a shared multi-dataset transformer. The idea is that the adapters make it possible to specialize to each dataset separately, while the transformer can model underlying task regularities. We train MADE in two phases. In the first phase, we jointly optimize the transformer and the adapters on all of the datasets. We create mixed training batches, like in multi-dataset training, but assign each example to the adapter from the corresponding dataset, and then backpropagate through both adapter and transformer parameters. After the average multi-dataset accuracy stops improving, we stop multi-dataset training and continue training the adapter separately. Here, we freeze the transformer parameters and train each adapter separately to find the best fit for each dataset. Here are the in-domain results on datasets from the MRQA 2019 shared task. First, here are the single dataset results, either with fine-tuning or with separate task-specific adapters. We can see that adapters generally work well for QA, which is consistent with prior results. Second, here are two multi-dataset models, multi-dataset fine-tuning and MADE without any separate adapter tuning. Multi-dataset training generally improves over single dataset training, although not in all cases. But when we add a second phase of adapter tuning to MADE, we consistently improve results. These results illustrate that both phases of training are important. Joint optimization improves results over single dataset models, and adapter tuning improves over multi-dataset models, while retaining a relatively low parameter footprint. Now we consider zero-shot generalization, where we want to predict answers for a new dataset that we haven't seen before. One issue we face is that MADE consists of multiple models, and we want to return a single answer, and ideally without having to do too many passes through a transformer. We find that a simple idea works surprisingly well. We create a new adapter, and we set the parameters by averaging the parameters of the different MADE adapters. Then use this new adapter to answer questions. We compare this approach to multi-dataset fine-tuning, to an equivalent collection of single-dataset adapters, and unified QA, which is a state-of-the-art text-to-text model trained on a variety of QA datasets. First, our multi-dataset baseline performs better than unified QA, which could be because the models were trained on different datasets and have slightly different architectures. Averaging the single dataset adapters tends to perform fairly poorly, but averaging the MADE parameters works well, outperforming all of the other models. This means we can turn our dataset experts into a single good general-purpose model. To look into these results more closely, we compare the zero-shot accuracy of the single dataset adapters, which were trained separately with a frozen transformer, with the MADE adapters, which were trained together with a transformer before being tuned separately. All of the MADE adapters generalize better than the single dataset adapters. The performance gap is considerably bigger than the gap in in-domain performance, and further illustrates the benefit of joint optimization. We can also see that averaging parameters improves results for the MADE adapters, but leads to a performance drop for the single dataset adapters. Finally, we consider a few-shot transfer setting, where we have access to a small number of training examples. We tried two transfer approaches. In the pre-averaging method, we initialize a new adapter like before using the weighted average of the MADE adapters, and train this new adapter on the training data. In the post-averaging method, we first train all of the adapters and the transformer on the training data, and then average the parameters at the end to get a single model to use for making predictions. Here are the transfer results averaged over the target datasets. And again, we compare unified QA, our multi-dataset baseline, and two methods for transfer learning with MADE. In the lowest data setting, all models struggle to learn, so MADE still performs the best on the basis of its strong zero-shot performance. With more training data, MADE still outperforms the other baseline, and both methods for transfer learning work equally well. With even more training data, the difference between the different models starts to get smaller, but MADE still performs well. In conclusion, MADE is a strong and versatile approach to modeling multi-dataset question answering, with good in-domain performance and good generalization and transfer. Our code and trained models are available on GitHub. Feel free to get in touch if you have any questions. Thanks.